On a clear night, if you step outside and let your eyes adjust to the dark, you can see roughly 5,000 stars with the naked eye. 5,000. It sounds like a lot. It is, by any human measure, a sky full of light. But those 5,000 stars are all within a few thousand light-years of Earth. A tiny bubble inside a galaxy containing somewhere between 150 billion and 250 billion stars total. You are seeing, on your clearest night, less than 100,000th of 1% of the stars in the Milky Way alone. And the Milky Way, as tonight will show you, is one of roughly 2 trillion galaxies in the observable universe. That number, 2 trillion, is where tonight's journey is headed. Not quickly, not in a way that asks anything of you other than to lie still and listen. We are going to walk outward together, one scale at a time, from the ceiling above you to the edge of everything that can be known. And then we are going to walk back, because the walk back is where the numbers stop being numbers and start being something else. Something closer to peace. You do not need to remember anything tonight. The facts are scaffolding. What matters is the feeling they build. And that feeling does not leave when the facts fade. Get comfortable. Let the weight of the day finish leaving your body. The universe has been out there for 13.8 billion years, and it is not going anywhere. We begin right here. Start with what is directly above you. A ceiling. Maybe. A roof. The open sky, if you happen to be outside. Whatever it is. That surface. That boundary between here and everything else is the beginning of tonight's journey. Not a metaphor, an actual starting point, because every distance we are going to explore, every scale that will quietly reshape the way you think about where you are, begins exactly here. Let us go up. The air between you and whatever is overhead has been cycling through lungs on this planet for hundreds of millions of years. The same oxygen that early mammals breathed, that every ancestor you have ever had breathed, is part of the atmosphere surrounding you right now. It does not feel ancient. It feels ordinary. That is one of the things about scale that tonight we'll keep returning to. The most extraordinary facts tend to wear the most ordinary clothes. The atmosphere does not end cleanly. It thins gradually as altitude increases, growing less dense with each mile, until it fades so completely that drawing a precise boundary between sky and space requires a decision rather than a measurement. The boundary most scientists and space agencies use is called the Kármán line, named after Theodor von Kármán, a Hungarian-American aerospace engineer who calculated in the mid-20th century that above roughly 62 miles altitude, the atmosphere becomes too thin for conventional aircraft to generate lift. It is a practical definition rather than a physical wall. Below it, you are in the sky. Above it, you are in space. The atmosphere itself continues thinning for thousands of miles beyond that line. But the Kármán line is where, by convention, the cosmos begins. 62 miles. On a clear, flat road, you could drive that distance in just over an hour. The boundary between your world and the rest of the universe is closer than most people driving to work. Above that line, the rules change. Sound stops traveling because there is almost nothing left to carry it. The sky, which has been shifting from blue to violet as you rise, goes fully black. Stars become visible even when the sun is shining, because there is no scattered atmosphere left to wash them out. And the curve of Earth becomes unmistakable. From 62 miles up, you can see, for the first time, that you are living on a ball. The International Space Station orbits at about 250 miles above the surface. The astronauts aboard it travel at roughly 17,500 miles per hour, completing one full orbit every 90 minutes. 16 sunrises, 16 sunsets, every single day. Think about that for just a moment. Not the speed, not the altitude, the sunrises. 16 times a day, the edge of Earth glows orange against the black, and then the sun appears. And then it sets again, and someone up there watches every single one of them. From their windows, the thin glowing stripe of the atmosphere is visible below, and nearly every astronaut who has seen it describes the same thing. Beautiful, yes, but also fragile looking. A painted line, impossibly thin, between everything alive and everything not. 250 miles is still, by the standards of what is coming, almost nothing at all. To reach the moon, you would need to travel roughly 240,000 miles from where you are lying right now. The moon is close enough that light reflecting off its surface reaches your eyes in just over 1 second. Close enough that the 12 human beings who walked on it between 1969 and 1972 could carry on real conversations with people on Earth. With only a brief delay, 3 days of travel each way, in the most powerful machines our civilization had ever built, to reach a world that light crosses in a single heartbeat. The moon is the only other world any human foot has ever touched. Everything else, every planet photographed up close, every moon mapped, every asteroid sampled, exists further away than that. Mars, at its closest, is still about 140 times farther than the moon. Jupiter is nearly 2,000 times farther. And beyond the planets, the distances stop being manageable in any way. Ordinary language handles well. The sky you can see on a clear night contains objects at wildly different distances, all flattened by your eye into the same apparent surface, like photographs pinned to a dark wall at different depths. The moon is a little over 1 light second away. The sun is about 8 light minutes away. The nearest star beyond our own is about 4.24 light years away, meaning the light you see from it tonight left it more than 4 years ago. And the faint smudge of the Andromeda Galaxy, just barely visible to the naked eye on the darkest nights, is about 2.5 million light years away. The light you see when you look at it left that galaxy long before modern humans existed on Earth. All of that lives in a single glance upward from your pillow. This is the thing about the sky that tends to get lost in the ordinary business of looking at it. It is not a flat surface scattered with lights. It is a window of enormous depth, and the objects visible through it are separated not by inches, but by years and centuries and millions of years of travel time. When you look up, you are looking back in time. The moon as it was a second ago. The sun as it was 8 minutes ago. The stars as they were years or decades or centuries ago. And Andromeda as it was 2.5 million years ago. Long before our species had words for any of it. Now here is something I want to hold before we go any further. We are not going to leave this room tonight. Not physically, but we are going to follow the scale of things outward. one step at a time, until the ceiling above you has been replaced by something that takes the rest of tonight to fully describe. And to do that properly, we need to understand something that took humanity a very long time to figure out. We need to understand how anyone knows how far away any of this actually is. Because for most of human history, no one did. The stars were lights, beautiful, reliable, useful for navigation across oceans and deserts and centuries. But how far away they were, what they actually were, whether the faint smudges, sometimes visible between them, were nearby clouds of gas or something else entirely, none of that was known. Learning to measure them is one of the great detective stories in the history of science. It begins with a shadow, and a woman working quietly in a room full of photographs, looking for a pattern that turned out to be a ruler long enough to measure the universe. Let your eyes stay closed. Let the room hold you. The universe has been out there for 13.8 billion years, and it will still be there when we continue. Take one slow breath. When you are ready, we follow the shadow. Try something right now, without moving. Hold one finger up close to your face. Close your left eye and notice where your finger sits against the wall behind it. Now, switch. Open your left eye. Close your right. Your finger appears to jump sideways, even though neither you nor your finger moved at all. The background shifted because you changed the angle of observation by a few inches. That small, effortless trick is the foundation of one of the most important techniques in the history of astronomy. It is called parallax, and for a long time, it was the only ruler astronomers had for measuring the distance to stars. As Earth travels around the Sun over the course of a year, it moves from one side of its orbit to the other, covering nearly 186 million miles between January and July. That shift in position changes the angle from which nearby stars appear against the much more distant background of the sky. A nearby star, observed in January and then again in July, appears to have moved slightly. The closer the star, the larger the apparent shift. By measuring that shift with precision, basic geometry gives the distance. In 1838, the German astronomer Friedrich Bessel successfully applied this technique to a star called 61 Cygni and calculated it was about 10 light-years away. His result was remarkably close to the modern measurement. For the first time in history, a human being had held a ruler up to the stars and gotten a real number back. But parallax has a limit. The farther a star is, the smaller its apparent shift becomes, until the shift is too small to measure accurately with any available instrument. Even today, with the most precise technology available, parallax only works reliably out to a few thousand light-years. The Milky Way is 100,000 light-years across. Parallax runs out of road very early, so astronomers needed a longer ruler. They found one, unexpectedly, in a blinking star, and the person who found it was working in conditions that, once you know about them, make the discovery feel even more extraordinary than it already is. In the early 1900s, a woman named Henrietta Swan Leavitt was working at the Harvard College Observatory, not as an astronomer in the traditional sense. She worked as a human computer, one of a group of women hired to analyze photographic plates of the night sky by hand, cataloging the brightness of stars one by one across thousands of glass images. The work was painstaking, poorly paid, and almost entirely invisible to the wider scientific community at the time. Leavitt was assigned to study a class of stars called Cepheid variables. These are stars that pulse in brightness in a regular rhythm, growing brighter and then dimmer over a cycle of days or weeks, as reliably as a slow heartbeat. What she discovered, published in 1912, was something no one had noticed before. The longer the period of a Cepheid's pulsation cycle, the more intrinsically luminous the star actually was. A Cepheid that takes 30 days to complete one cycle is genuinely brighter than one that takes 10 days. The rhythm and the true brightness were locked together in a precise and usable relationship. This was a ruler, a cosmic one. If you know how bright a star truly is, and you can measure how bright it appears from Earth, the difference between those two values tells you how far away it must be. Bright things look dim at distance in a mathematically predictable way. Leavitt had turned Cepheid variable stars into what astronomers call standard candles, objects of known true brightness, so that apparent brightness becomes a measuring tape stretching across distances that parallax could never reach. Using this technique, an astronomer named Edwin Hubble did something in 1923 that quietly changed humanity's understanding of everything. He identified individual Cepheid stars inside a faint smear of light in the constellation Andromeda, a smear that had been debated for decades. By measuring the periods of those Cepheids and applying Leavitt's relationship, he calculated the distance. It was not inside the Milky Way. It was roughly 900,000 light-years away, a distance so large it placed the smear entirely outside our galaxy. The Andromeda Nebula, as it had been called, was not a nebula at all. It was an entire galaxy, a separate island of hundreds of billions of stars, at an enormous distance, entirely independent. And if Andromeda was its own galaxy, then every other faint smear scattered across the sky was almost certainly one too. The universe was not one galaxy surrounded by empty space. It was filled with galaxies. The scale of everything had just increased by a factor that most human minds, in 1923, were not remotely prepared for. Hubble went further, studying the light from dozens of distant galaxies. He found a pattern. The light from almost every galaxy showed a shift toward the red end of the spectrum. And the farther away the galaxy, the larger that shift. This redshift is the signature of recession, the same way the pitch of a passing siren drops as it moves away from you. Light stretches toward longer, redder wavelengths when its source is moving away. Nearly every galaxy in the universe was receding from us, and the more distant ones were receding faster. This was not galaxies flying apart through space like fragments from an explosion. It was space itself expanding. The fabric of the universe was stretching, carrying the galaxies with it. The way raisins in a rising loaf of bread move apart from each other, not by swimming through the dough, but because the dough itself is growing. Hubble published this in 1929. It became one of the foundational observations of modern cosmology. It told us the universe had a beginning, a moment when everything was compressed together, and has been expanding outward ever since. The chain of measurement built on these discoveries, from the geometric trick of a shifted finger to the blinking stars Leavitt decoded to the redshift of entire galaxies, is what astronomers call the cosmic distance ladder. Each rung carries you farther than the one below, and each rung depends on the accuracy of everything beneath it. It is a structure built over centuries by thousands of people, many of them, like Henrietta Swan Leavitt, working quietly in roles that history was slow to honor. I think about Leavitt sometimes when I think about the scale of the universe. Working with glass plates and a magnifying lens, cataloging brightness by hand, she found something hidden in the data that stretched far enough to measure the cosmos. The right question, asked carefully enough, can outreach any instrument. The ladder is built. The distances are ready. Now we climb. Before we climb very far, we need to spend some real time with the place we are climbing from. The solar system is the only home our species has ever known. Every human being who has ever lived was born here, spent their entire life here, and died here. The 12 astronauts who walked on the moon stepped onto the only other world a human foot has ever touched. And even they came back. Everything you have ever eaten, every road ever built, every conversation ever had, every ordinary Tuesday afternoon, every extraordinary moment of any kind, happened within the gravitational embrace of one middle-aged star in one quiet region of one galaxy. It is worth knowing what that home actually looks like. At the center sits the Sun. It contains 99.8% of all the mass in the entire solar system. Everything else. All 8 planets. All their moons. All the asteroids and comets, and dust, and the distant frozen objects of the outer reaches makes up the remaining 0.2%. The Sun is so dominant that describing the solar system as a star with some planets is more accurate than describing it as a star and its planets. Everything else is, in the most literal gravitational sense, debris orbiting a fire. The Sun itself is large by any human standard. Its diameter is about 109 times the diameter of Earth. If it were hollow, you could fit roughly 1,300,000 Earths inside it. And yet, by the standards of the stars in our galaxy, the Sun is a perfectly ordinary, medium-sized star. Not large, not small, not especially young or old. A yellow dwarf about 4.6 billion years into what is expected to be a roughly 10 billion year lifespan. We are in the middle of it. Earth orbits the Sun at an average distance of about 93 million miles. This distance is used so often in astronomy that it has its own unit, 1 astronomical unit, or 1 AU, simply means the average Earth-Sun distance. A convenient yardstick for describing distances within the neighborhood. On that scale, Mercury orbits at about 0.4 AU, Venus at 0.7, Mars at 1.5, then a gap before the giant planets, Jupiter at 5.2 AU, Saturn at 9.5, Uranus at 19, Neptune, the outermost of the 8 recognized planets, at about 30 AU. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies extending out to perhaps 50 AU. And beyond that, the much more diffuse theoretical structure called the Oort cloud, a shell of cometary bodies that may extend anywhere from around 2,000 to 100,000 AU from the Sun. The solar system does not end at a clean line. It fades, gradually, into interstellar space. The place where the Sun's direct influence finally gives way to the interstellar medium is called the heliopause. Voyager 1, the most distant human-made object ever launched, crossed the heliopause in 2012. after 35 years of continuous travel. At the time of crossing, it was about 121 AU from the Sun. 35 years. 121 AU. The nearest star, Proxima Centauri, is about 268,000 AU away. The heliopause sits at roughly 0.045% of the distance to the nearest star. Our entire solar system, the full span of planetary orbits, and the vast surrounding cloud of icy objects, occupies a bubble that is less than 0.1% of the way to our nearest neighbor. Let us make that concrete with a scale model, because these numbers have a way of being heard without being felt. Imagine shrinking the solar system so that the distance from Earth to the Sun becomes the length of a single grain of rice, about 6 millimeters. On that scale, Mercury sits about 2.5 millimeters from the Sun. Neptune, the outermost planet, sits about 18 centimeters away. The entire sweep of planetary orbits fits within roughly the span of your open hand. Now, on that same scale, where is the nearest star? About 1.7 kilometers away. More than a mile. Everything our spacecraft have ever visited. Every planet ever photographed up close. Every moon ever mapped. Every asteroid ever touched by a human-made object fits in the palm of your hand. And the nearest star is over a mile away in this model, separated from your palm by a gap containing almost nothing at all. Not empty in a dramatic sense, just very, very thinly scattered atoms and the occasional particle drifting on the solar wind. Almost nothing. For over a mile, before you reach the next grain of rice. And that mile is just to the nearest one. The Milky Way contains somewhere between 150 billion and 250 billion stars. If our scale model solar system fits in the palm of your hand, the Milky Way, on the same scale, would stretch roughly the distance from New York City to Los Angeles and back. Twice. The entire width of a continent. In both directions. Every star in that span, separated from its neighbors by similar miles of almost nothing. We have just run out of useful comparisons. The scale has quietly exceeded anything a household object can represent. This is a feeling worth staying with rather than rushing past. Not because it is frightening, because it is honest. And the honest picture of where we are is the foundation of everything else tonight is built on. But before we zoom out to the full scale of the Milky Way, there is something here in the solar system I want to leave you with. Something that tends to get lost in the rush toward bigger and bigger numbers. This small address is extraordinary. The particular distance of Earth from the Sun places liquid water on its surface. The particular size of Earth gives it enough gravity to hold an atmosphere, but not so much that it crushes complex chemistry. The presence of a large moon stabilizes the tilt of Earth's axis, giving the planet relatively predictable seasons across geological time. Jupiter, sitting out in the middle of the solar system, has over billions of years influenced the trajectories of many objects that might otherwise have struck the inner planets far more frequently. Science does not claim any of this was arranged for us. What the evidence does show is that the specific, particular, unrepeatable arrangement of this small corner of one galaxy has, over 4.5 billion years, produced conditions in which something like tonight is possible, in which a living creature can lie in the dark, breathe, and wonder about the size of everything. That is not a small thing to be. The palm of your hand contains everything we have ever directly visited. The rest is inference and light. Extraordinary inference. Extraordinary light. But we have never left the grain of rice. Not yet. Step back now. Far back. Far enough that the sun becomes just another point of light. We are going to try to see the Milky Way whole. And the first honest thing to say about that attempt is that it comes with a difficulty no other chapter tonight shares. We have never seen it from the outside. No spacecraft we have ever built has traveled even a fraction of the distance needed to look back at our galaxy as a whole. Every image you have ever seen labeled as a photograph of the Milky Way is either a picture of a different galaxy entirely, or an artist's reconstruction built from data. We are mapping the house we live in from inside one of its rooms, measuring the walls we can reach, and inferring the ones we cannot see. This is worth knowing, not because it undermines what we understand, but because it is one of the most remarkable examples of what science actually does. We know a great deal about the Milky Way, not despite being inside it, but through the patient work of piecing together millions of individual measurements into a coherent picture. The picture is genuinely good. It is also genuinely incomplete, and scientists say so openly. With that honesty in place, here is what we know. The Milky Way is a barred spiral galaxy. At its center is a structure shaped roughly like a bar, from which spiral arms extend outward and curve away into space. From above, if we could ever see it from above, it would look something like a slow pinwheel. A bright, dense center. A bar of stars through the middle. 4 main spiral arms curling outward, trailing stars and gas and dust in long, sweeping curves. The disk of the galaxy is approximately 100,000 light-years across. Some recent studies using data from the European Space Agency's Gaia mission, which has been mapping the positions and motions of nearly 2 billion stars with extraordinary precision, suggest the disk may extend somewhat further in certain directions. But 100,000 light-years is a well-supported central estimate. In terms of thickness, the disk is much thinner than it is wide, roughly 1,000 light-years in its thinnest layer, more like a vinyl record than a ball. Extraordinarily flat for something so large. At the very center sits a structure called the galactic bulge, a roughly spherical concentration of older stars glowing at the heart of the disk. And at the very center of that bulge, lurking behind thick clouds of dust and gas that block visible light entirely, sits Sagittarius A star, our galaxy's supermassive black hole. In May of 2022, the Event Horizon Telescope collaboration released the first direct image of it, a glowing ring of superheated gas surrounding a dark central shadow, exactly as the physics had predicted. For the first time, human beings directly saw the object sitting at the gravitational heart of the galaxy they were born in. Its mass is approximately 4 million times the mass of our Sun. Our Sun sits nowhere near the center. It occupies a relatively modest region called the Orion Arm, about 26,000 light-years from the galactic center, a little over halfway out from the center to the edge of the disk. In a quiet stretch of one of the galaxy's less dramatic spiral arms, this position turns out to be significant in ways that go beyond mere geography. The inner regions of the galaxy are more crowded with stars and more frequently disturbed by energetic events. The outermost regions have fewer of the heavy elements that rocky planets require, because those elements are forged inside stars and distributed by supernova explosions over billions of years. And, The outer galaxy has had fewer of both. Our intermediate position, far enough from the center to avoid its hazards, but close enough to benefit from billions of years of stellar chemistry, places us in what some researchers have called a galactic habitable zone. The Milky Way contains somewhere between 150 billion and 250 billion stars. The uncertainty reflects the genuine difficulty of counting objects hidden behind dust and spread across 100,000 light-years. What every method agrees on is that the number is very, very large. Now, let us feel the size of this one more time, because the numbers keep needing to land differently before they actually land. Light travels at about 186,000 miles per second. In 1 year, it covers about 5.9 trillion miles. The Milky Way disk is 100,000 light-years across. That means light, traveling at the fastest speed anything in the universe can travel, would take 100,000 years to cross our galaxy from edge to edge. The Parker Solar Probe, the fastest object our civilization has ever built, reached speeds of about 430,000 miles per hour during its closest solar approaches in late 2024. At that speed, crossing the Milky Way would take approximately 250 billion years. The current age of the universe is about 13.8 billion years. We would need to run the universe roughly 18 more times, from the Big Bang to today, to cross our own galaxy in our fastest machine. This is not the universe. This is just our island. Beyond the disk and the bulge, the Milky Way is surrounded by a vast, roughly spherical structure called the stellar halo, containing older stars and ancient globular clusters, those compact balls of tens of thousands to millions of stars that orbit the galaxy in long looping paths. And surrounding all of that, extending much further still, is the dark matter halo, an invisible gravitational structure estimated to reach perhaps 100,000 to 300,000 light-years from the center. The galaxy, we can see, is floating inside a much larger structure we cannot see directly at all. This will matter more in a few chapters. For now, hold this: 100,000 light-years of stars, gas, ancient light, and invisible dark matter, rotating slowly around a supermassive black hole that was photographed for the first time just a few years ago, located in a universe we have not yet begun to describe at its full scale. And this island is not alone. On a clear night in the southern hemisphere, away from city lights, two faint smudges are visible near the constellation Dorado. They look at first like detached fragments of the Milky Way, loose pieces broken away from the great band of light arching across the sky. For thousands of years, the indigenous peoples of the southern hemisphere knew them well and wove them into their navigation and their stories. European sailors used them as reliable markers of the southern sky. Ferdinand Magellan's crew observed and recorded them during the first circumnavigation of Earth in the early 1500s, and his name became attached to them. They are not clouds. They are galaxies. The Large Magellanic Cloud sits about 160,000 light-years from Earth. The Small Magellanic Cloud, about 200,000 light-years away. Both are gravitationally bound to the Milky Way, orbiting our galaxy in long sweeping paths that have brought them close enough to be visible as soft glows in the unaided eye from anywhere in the southern hemisphere on a dark night. Take a moment with that. You can see another galaxy without a telescope, not a point of light, not a star, an entire galaxy containing billions of stars, visible as a soft blur to anyone who looks up in the right place on the right night. The Large Magellanic Cloud contains roughly 30 billion stars by current estimates. The Small Magellanic Cloud, perhaps 3 billion, each one an entire world system of stellar complexity. Sitting close enough to see with the same eyes that read faces and find shapes in clouds. Both are irregular galaxies, their shapes lumpy and chaotic, pulled and distorted by the gravitational influence of the Milky Way across billions of years of close interaction. That interaction has left a visible record. There is a structure called the Magellanic Stream, a long ribbon of hydrogen gas stretching across a vast arc of the southern sky, pulled out from the Magellanic Clouds by tidal forces during their close approaches to our galaxy. Discovered by radio astronomers in the 1970s, it represents an enormous ongoing transfer of material between galaxies, not a sudden event, a slow gravitational conversation written in hydrogen gas across hundreds of thousands of light years. The Milky Way has other satellite galaxies beyond the Magellanic Clouds. Current estimates suggest somewhere in the range of 50 to 60 confirmed satellites orbit our galaxy. Most of them small dim objects called dwarf galaxies. Several of the nearest are in the process of being gradually pulled apart and absorbed. The Sagittarius dwarf galaxy, discovered in 1994, sits partially hidden behind the bulk of the Milky Way itself, currently being torn into long streams of stars that wrap around our galaxy. What was once a separate, independent galaxy is, in slow motion, becoming part of us. This has happened before, many times. The Milky Way we live in today is not the galaxy that existed 10 billion years ago. It has grown through mergers and absorptions, pulling in smaller galaxies, incorporating their stars and gas and dark matter. Some of the stars in our galaxy's halo are almost certainly former residents of galaxies that no longer exist as independent objects anywhere in the universe. The Milky Way consumed them. The galaxy is not a fixed object. It is a process. And the process is not finished. The Large Magellanic Cloud, according to some current models, based on measurements of its velocity and mass, may itself eventually merge with the Milky Way in the range of 2 to 3 billion years from now. The timing and details remain subjects of active research, but the general direction is consistent with what the observations show. Step back now and look at the Milky Way system as a whole. The galaxy itself, 100,000 light-years across. Its dark matter halo extending perhaps 2 to 3 times that distance. A swarm of satellite dwarf galaxies orbiting in paths taking them anywhere from tens of thousands to hundreds of thousands of light-years from the center. Long streams of stars trailing behind the closest ones, marking their orbital paths like contrails in the dark. This entire system already exceeds ordinary human experience by such a margin that comparisons almost refuse to form. And yet it is, by the standards of what we are about to encounter, a single point in a much larger structure. The Milky Way is not alone the way a lone island is alone in the ocean. It is alone the way one house is alone among other houses on a very long street. The neighbors are out there. We can see them, and the street, as we are about to discover, is longer than anything we have tried to describe so far tonight. Let your breathing slow. 2 faint smudges in the southern sky, billions of stars in each of them, close enough to be falling toward us in gravitational arcs that will take billions of years to complete. The nearest galaxies, already in motion, already in conversation with our own. The universe is not a still photograph. It is a slow dance. And we are in the middle of it. Imagine standing on a street at night and looking down the block. The houses nearest to you are the ones you know best. You can see their lights. Notice when something changes. Watch the seasons move across their gardens. Further down, the details blur. Beyond a certain point, the street curves away, and you cannot see how far it continues. The local group is the street our galaxy lives on. It is a collection of galaxies bound together by their mutual gravity, moving together through the larger universe as a single gravitational system. The term was coined by Edwin Hubble in 1936. Today, with far more sensitive instruments and decades of additional surveys, the local group is known to contain more than 50 confirmed galaxies, with new small members still being found as telescope technology improves. The local group spans roughly 10 million light-years from one end to the other. Pause on that. The Milky Way is 100,000 light-years across. The local group is about 100 times wider than the galaxy it contains. We have just stepped up by a factor of 100. And we are still, as we will eventually discover, inside one of the smallest identifiable structures in the universe. The local group is dominated by two large spiral galaxies. One is the Milky Way. The other is Andromeda, known to astronomers as M31. These two are by far the most massive members, and the gravitational dynamics of the entire local group are largely shaped by the relationship between them. Andromeda sits at a distance of approximately 2.5 million light-years. It is the most distant object visible to the naked eye under truly dark skies, appearing as a faint, elongated smudge in the constellation that shares its name. That faint smudge is an entire galaxy. It contains somewhere in the range of 1 trillion stars, making it somewhat larger and more massive than the Milky Way by most current estimates. And it is heading toward us. The collision between the Milky Way and Andromeda is one of the most well-documented future events in astronomy. Measurements of Andromeda's velocity, refined using data from the Hubble Space Telescope and the Gaia mission, indicate it is approaching at roughly 110 kilometers per second. At that rate, the two galaxies are expected to begin their first close encounter in approximately 4.5 billion years, with a full merger likely completing several billion years after that. This might sound alarming. It is not. Galaxies are mostly empty space. The stars within them are separated by such enormous distances that even when two galaxies pass through each other, the probability of any two individual stars actually colliding is extremely small. What happens instead is gravitational. The two galaxies distort each other, pulling out long tidal streams of stars, triggering new star formation as gas clouds are compressed by the interaction. And gradually, over billions of years, merging into a single new structure. But here is the part worth sitting with. In the night sky above any world, still orbiting our sun during the merger, Andromeda will no longer be a faint smudge. It will be a galaxy, fully visible, filling a wide arc of the sky. Its spiral arms and bright core visible without any instrument at all, growing slowly brighter and larger over millions of years as the two systems draw together. Two galaxies occupying the same sky. the light of 2 trillion stars combined, visible on any clear night, for anyone alive to see it. The result of the merger, once the gravitational reshaping is complete, is expected to be a large elliptical galaxy, a slowly rotating cloud of stars without the elegant spiral arms that both currently display. Our Sun will almost certainly survive. It will likely end up somewhere very different within the merged system than it sits today. And the night sky, eventually, will be changed in ways that would be unrecognizable to anyone alive right now, 4.5 billion years away. For tonight, Andromeda is just that faint smudge, 2.5 million light-years distant, carrying 1 trillion stars slowly toward us in a dance that began long before our Sun was born. The third largest member of the local group is the Triangulum Galaxy, M33, a spiral about 3 million light-years away, containing perhaps 40 billion stars. Beyond these three, the rest of the group consists mostly of dwarf galaxies scattered around the 2 dominant spirals, all of them gravitationally bound, all of them held together against the general expansion of the universe by their mutual gravity. That last detail matters. Inside the local group, gravity wins over expansion. These galaxies will not be carried apart. Their future is convergent. They will merge and reorganize over billions of years rather than drift into isolation. The local group is one of the largest scales at which gravity holds things together against the outward push of the expanding cosmos. We have traveled 10 million light-years from home and barely left the neighborhood. 54 galaxies in a gravitational family, one small corner of something enormously larger. The street we live on, just wait until you see the city. For most of the 20th century, astronomers thought galaxy clusters were the largest distinct structures in the universe. A cluster might span anywhere from a few million to 30 or 40 million light-years, containing hundreds to thousands of galaxies bound together by gravity. The local group, spread across 10 million light-years, is actually a relatively small and sparse cluster by galactic standards. Larger clusters, like the Virgo cluster, sitting about 53 million light-years from the Milky Way, contain thousands of galaxies in a comparable span. For a while, clusters seemed like the top of the hierarchy. Then, astronomers began mapping galaxy positions across larger and larger volumes of space. And something new emerged from the data. Clusters were not the biggest things. They were components of something larger, something that did not even have a widely agreed name until fairly recently. Superclusters, collections of galaxy groups and clusters spread across regions hundreds of millions of light-years wide, loosely connected by gravity and the geometry of the universe's matter distribution. For decades, the Milky Way was understood to sit within one called the Virgo Supercluster, named for the Virgo cluster near its center. The Virgo Supercluster spans roughly 110 million light-years and contains an estimated 100 to 200 galaxy groups and clusters, of which our local group is one small member near the outskirts. Then, in 2014, a team led by R. Brent Tully of the University of Hawaii published a paper in the journal Nature that redrew the map entirely, using a new technique that analyzed not just the positions of galaxies but their velocities, specifically the way those velocities deviated from the smooth expansion of the universe. Tully and his colleagues mapped the gravitational landscape of a much larger region. Galaxies flow toward regions of high mass concentration, the way water runs downhill, By tracing those flows across an enormous volume of space, the team could identify the full basin of gravitational attraction within which our galaxy sits. What they found was that the Virgo supercluster is not an independent structure at all. It is one lobe of a vastly larger supercluster they named Laniakea. From the Hawaiian, it means immeasurable heaven. Laniakea spans approximately 520 million light-years. It contains the mass of roughly 100 million billion suns. It includes approximately 100,000 galaxies organized into a complex web of filaments and sheets, all of them flowing toward a central gravitational region the researchers called the Great Attractor. Let that name sit for a moment. The Great Attractor, not a poetic invention, a real region of space. Sitting roughly 250 million light-years from the Milky Way in the direction of the constellations Centaurus and Norma, toward which an enormous volume of the universe is slowly being drawn, the gravitational pull of the mass concentrated there is strong enough to influence the motion of galaxies across hundreds of millions of light-years. We are falling toward it, very slowly, from very far away, but falling. The discovery of Laniakea required stepping back far enough to see something invisible at smaller scales. From inside the Virgo supercluster, the galaxies around us looked like a cluster with some extensions. Seen at the scale of 500 million light-years, those extensions revealed themselves as tributaries, all flowing into a much larger river system, draining toward the same gravitational center. I find something quietly staggering about that image every time I return to it. Not frightening, staggering in the way that something genuinely true and genuinely large tends to be. When you stop letting the numbers slide past and actually let them press on you for a moment. Now try to hold the scaling we have done together tonight. The Milky Way is 100,000 light-years across. The local group is 10 million light-years across. 100 times bigger, Laniakea is 520 million light-years across. 52 times bigger than the local group, about 5,000 times bigger than the Milky Way. If the Milky Way were a single grain of sand, Laniakea on the same scale would be roughly 5 meters across, about the width of a large room. Every grain of sand in that 5-meter span would be an entire galaxy, 100,000 galaxies. In a room, each one a grain of sand. And Laniakea is one feature in a pattern covering the entire observable universe. There is a quality to this kind of scaling that keeps appearing tonight and deserves to be named directly. Each time we step back far enough to see a new level of structure, what looked like the whole picture reveals itself as one small part of something larger. The solar system inside the galaxy inside the local group inside Laniakea. This is not a trick of perspective or a sign that the universe is trying to overwhelm us. It is a genuine feature of how matter is organized in the cosmos. A nested hierarchy assembled by gravity acting over billions of years on the initial conditions of the universe. Understanding this hierarchy changes the way the night sky feels. The faint smudges visible through a telescope are not random. They are organized. They form walls and sheets and filaments and clusters with vast empty spaces between them. And those arrangements reflect processes that began when the universe was less than a second old. The universe has a texture, and to see that texture clearly, we need to zoom out one more time, past the scale of superclusters, into the largest patterns that have ever been mapped. Rest here for just a moment. you are at one address inside a grain of sand galaxy. Inside, a local group 10 million light-years wide. Inside a Laniakea 520 million light-years across, falling slowly toward the Great Attractor, along with 100,000 other galaxies, most of whose names no human being has ever spoken. The next step is the largest one we will take tonight. There is an image that astronomers return to again and again when they try to describe what the universe looks like at its largest scales. A spider's web seen in early morning light, heavy with dew, each thread lined with droplets. Where threads meet, the droplets cluster into larger beads. Between the threads, nothing, just open air, held in shape by the geometry of what surrounds it. The universe, mapped at its largest scales, looks almost exactly like that web. This is not a poetic exaggeration. It is one of the most striking confirmed results in modern cosmology, reproduced across decades of galaxy surveys using increasingly powerful instruments and increasingly comprehensive sky coverage. When you plot the positions of millions of galaxies across hundreds of millions of light-years, what emerges is a pattern of extraordinary consistency, long filaments of galaxies stretching across space, flat sheets where filaments intersect, dense clusters at the nodes where multiple filaments meet, and between all of it, vast regions containing almost nothing at all. Astronomers call this the cosmic web. To understand how it came to exist, we need to go back to the very beginning. Not far back in the sense of a long detour, far back enough to feel the thread that connects what you see in tonight's sky to the first moments of the universe. When the universe was very young, less than 400,000 years old, it was filled with an extremely hot, dense plasma of particles and radiation, all locked together. Within this plasma were tiny variations in density, quantum fluctuations from the universe's earliest moments that had been stretched to enormous scales. These variations were extraordinarily small, but gravity is patient. Over hundreds of millions of years, those slight over-densities began attracting more matter. Gas flowed toward denser regions. The denser regions grew denser still. The underdense regions, now called voids, grew emptier. Gravity amplified the initial pattern, turning tiny ripples in the newborn universe into the full structure of the cosmic web over billions of years. The result is what we see today. Roughly half of all visible matter in the universe is concentrated in filaments and sheets that occupy only a small fraction of total volume. Vast voids, containing very few galaxies, fill most of the space. A typical cosmic filament stretches for hundreds of millions of light-years, a river of galaxies flowing along a gravitational channel, clustering more densely where the filament thickens and bunching into massive concentrations at the nodes where filaments intersect. The voids between them are equally remarkable. A typical cosmic void spans 200 to 300 million light-years across. Inside these voids, galaxies are extremely rare, not completely absent. Small galaxies and isolated structures do exist within them, but the contrast between the density of matter inside a filament and inside a void is enormous. If you were somehow placed inside a large cosmic void, the nearest galaxies would be very faint and very distant. The sky would be darker and emptier than anything we experience from our position in a modestly populated filament. The first systematic evidence for the cosmic web emerged from galaxy surveys beginning in the 1980s, with the CFA Redshift survey producing the first clear visual maps of filaments and voids. The Sloan Digital Sky Survey in the late 1990s and 2000s mapped millions of galaxies and revealed the web in striking detail. More recently, the Dark Energy Spectroscopic Instrument at Kitt Peak National Observatory in Arizona is extending these maps to greater depths, building the most comprehensive three-dimensional picture of the cosmic web ever assembled. Some of the largest individual structures identified in the observable universe are features of this web. The Sloan Great Wall, identified in 2003, is a sheet of galaxies approximately 1.4 billion light-years long. The Hercules Corona Borealis Great Wall, reported in 2013, is proposed to span roughly 10 billion light-years, which, if confirmed as a single coherent structure, would make it the largest known feature in the observable universe. Its status remains a subject of active scientific discussion, with researchers continuing to study whether it represents one unified structure or a statistical pattern in the data. The cosmic web is not static. It is evolving. Filaments are slowly draining matter into the massive nodes at their intersections. Voids are slowly growing emptier. Gravity is continuing the work it began when the universe was less than a second old, organizing and concentrating matter into ever tighter structures, while the spaces between them grow ever more vacant. The universe is still under construction. There is something about the image of the cosmic web that almost everyone describes in similar terms when they encounter it for the first time. It does not look like something you would expect pure physics to produce. It looks organic. It looks like the kind of structure biology makes. Several studies have formally compared its statistical properties to the neural network of the human brain and found striking mathematical similarities in their organizational geometry. This does not mean the universe is a mind. It means certain principles of network organization appear across very different physical systems at very different scales, which is itself a remarkable observation about the way nature builds things. I have spent time looking at images of the cosmic web, and I still find it quietly astonishing each time. There is something in the pattern that feels like recognition, like the universe is repeating a principle it finds useful over and over, at scale after scale after scale. And all of this, the entire cosmic web, with its filaments and voids and great walls, exists within the observable universe, a region of space defined not by any physical boundary, but by the distance light has had time to travel since everything began. That boundary is where we are headed next. What lies at it, and what may lie beyond it, is one of the most honest and affecting ideas that modern cosmology has to offer. Let the image of the web settle gently. Threads of galaxies stretching across hundreds of millions of light years. Enormous dark voids between them, patient and quiet. And somewhere in a modest filament of a modest supercluster, one small spiral galaxy, carrying one small planet, carrying you, lying in the dark, listening to the universe describe itself. The web holds everything, and you are woven into it. There is a word in the language of cosmology that carries more weight than it first appears to: observable. When astronomers say the observable universe, they do not mean the part of the universe that telescopes have gotten around to examining so far. They mean something more fundamental. The region from which light has had enough time, given the age of the universe, to reach us. It is not a technological limit waiting to be overcome by better instruments. It is a physical one, written into the structure of reality itself. And understanding why it exists and what it truly means opens one of the most genuinely strange doors in all of science. The universe is approximately 13.8 billion years old. This age is known with considerable precision from multiple independent lines of evidence, including the detailed structure of the cosmic microwave background, the abundance of light elements formed in the first minutes after the Big Bang, and the measured expansion rate of the universe. 13.8 billion years is not a rough estimate. It is a measurement, refined over decades of observation and confirmed repeatedly by different methods. Now, you might expect that if the universe is 13.8 billion years old, the observable universe should have a radius of 13.8 billion light-years. Light traveling since the beginning, in every direction, would have covered 13.8 billion light-years in 13.8 billion years. Simple enough. But the observable universe is not 13.8 billion light-years in radius. It is approximately 46.5 billion light-years in radius, making it about 93 billion light-years in diameter. That discrepancy is not an error. It is a consequence of expansion, and following the logic of it carefully is one of those moments where physics reveals itself to be stranger and more interesting than common sense would ever suggest. When light left a very distant region of the universe shortly after the Big Bang, that region was much closer to us than it is today. Space has been expanding throughout the entire time that light has been traveling toward us. So while the light was in transit, the region that emitted it was being carried further away. By the time the light arrives at our telescopes, the object that emitted it is much farther away than the time the light has been traveling would suggest. Light that has been traveling for 13.8 billion years reaches us from a source that is now approximately 46.5 billion light-years away, because the space between us and it has been stretching the whole time. This is not a violation of any physical law. It is not the source moving through space faster than light. It is space itself expanding, carrying the source with it. Very distant regions of the observable universe are receding from us faster than the speed of light. Not because they are moving through space quickly, but because the volume of space between us and them is growing so rapidly. We can still receive their ancient light because that light was emitted when they were much closer and has been traveling toward us ever since. Even as the source continues to move away, the boundary of the observable universe corresponds to a specific moment in cosmic history. About 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was so hot and dense that light could not travel freely. It was constantly scattered by the plasma, the way sunlight scatters inside a thick fog. When neutral atoms formed, the fog cleared. Light was free to travel for the first time in cosmic history. The light released at that moment has been traveling ever since. It reaches us today, stretched by nearly 14 billion years of expansion into the microwave part of the spectrum, as a faint glow filling the entire sky equally in every direction. Not from one source, from everywhere, simultaneously, a sphere of ancient light surrounding us completely, the oldest electromagnetic signal in the universe, arriving from all directions at once. This glow is called the cosmic microwave background. It was first detected in 1964 by Arno Penzias and Robert Wilson, two radio astronomers working at Bell Labs in New Jersey. They were trying to track down an unexplained, persistent hiss in a large horn-shaped antenna originally built to support early satellite communications. They checked everything. They checked the electronics, recalibrated the instruments, accounted for every known source of interference. They found pigeons nesting inside the antenna and removed them, cleaning out what they described in their notes, with wonderful understatement. As a white dielectric material, the hiss persisted through everything. It came equally from every direction in the sky, regardless of where the antenna was pointed, regardless of the season, regardless of the time of day. It was not noise. It was the oldest light in the universe, the afterglow of the Big Bang itself, arriving from every direction simultaneously because it surrounds us completely. Penzias and Wilson had no idea what they had found. It was a physicist at Princeton named Robert Dick, working independently to try to detect exactly this signal, who recognized it when Penzias called him. Dicker is said to have put the phone down and told his colleagues, simply, that they had been scooped. Penzias and Wilson received the Nobel Prize in Physics in 1978. What they stumbled onto while trying to clean a radio antenna became one of the most important observational confirmations in the history of cosmology. In the decades since, the cosmic microwave background has been mapped with extraordinary precision. NASA's COBE satellite in the early 1990s, the WMAP mission in the 2000s, and most recently the Planck satellite operated by the European Space Agency, whose final results were published between 2015 and 2018. These maps reveal tiny temperature fluctuations in the background radiation, variations of only about 1 part in 100,000 that correspond to the density variations in the early universe that eventually grew under gravity into the cosmic web we explored in the last chapter. The cosmic microwave background is a baby picture of the universe, a snapshot of everything when it was 380,000 years old, preserved in light that has been traveling ever since. Beyond it, we cannot see, not because nothing is there, because the universe before that moment was opaque to light, and no direct electromagnetic record of it survives for us to receive. Whatever happened in those first 380,000 years, the processes that set the initial conditions of everything we can observe, left no direct light for any telescope to find. So the observable universe has a genuine horizon, not a wall, not a place where space ends, a limit to what any observer, anywhere, can know through light. And that horizon, 46.5 billion light-years away in every direction, defines a sphere of knowable cosmos centered on wherever you happen to be. This leads to something I find genuinely affecting once it settles in fully. Every observer, wherever they are in the cosmos, has their own observable universe. An astronomer in a galaxy on the far side of Laniakea would have an observable universe centered on their location, extending 46.5 billion light-years in every direction from them. Their sphere and ours would overlap substantially, but not completely. There would be regions they can see that we cannot, regions we can see that they cannot. The universe has no single privileged vantage point, no center that sees everything. Every location is the center of its own observable sphere. Every observer, everywhere, is surrounded by a horizon they cannot see beyond, not because of the limits of their instruments, but because of the age of the universe and the speed of light. These are not walls that technology will ever move. Now, what lies beyond our horizon? The honest answer is that we do not know, and depending on how the universe is structured, we may never know in any direct observational sense. No telescope, however powerful, can show us what light has not yet had time to bring us. What physics can offer are models, tested against what we can observe, and then carefully extended beyond. The geometry of the observable universe, measured in extraordinary detail by the Planck satellite, is consistent with a spatially flat universe. Flat means the large-scale geometry of space does not curve back on itself the way the surface of a sphere does. A flat universe is mathematically consistent with being infinite, though it does not require it. If the universe is infinite and flat, there is simply more universe beyond our horizon, extending without boundary in every direction, containing more galaxies, more filaments and voids, more stars and planets and whatever else the universe produces, in a volume with no edge and no end. Some cosmologists argue that in a truly infinite universe, every physically possible arrangement of matter will exist somewhere. This is a legitimate extension of the geometry measurements, held as theoretical reasoning rather than confirmed observation. It is the kind of idea that rewards sitting with rather than rushing through, not because it can be verified, but because it honestly represents the edge of what current science can responsibly say about what might lie beyond what we can see. Other frameworks go further. The theory of cosmic inflation, first proposed by Alan Guth of the Massachusetts Institute of Technology in 1981 and developed substantially since, proposes that the very early universe underwent a period of extraordinarily rapid expansion in a tiny fraction of a second. Inflation is supported by observational evidence, most notably its predictions about the pattern of fluctuations in the cosmic microwave background. Some versions of inflation theory suggest the inflationary process may not stop everywhere simultaneously, potentially producing separate regions of the universe, each with their own properties. These ideas are pursued seriously by physicists at major institutions and published in peer-reviewed journals. They are also currently beyond direct observational confirmation. They are seriously considered theoretical possibilities, not established features of the cosmos. What we can say with confidence is this: the observable universe is not thought to be the entirety of what exists. The full universe is very likely larger. How much larger? In what form? With what contents? We cannot say. Holding that uncertainty honestly, without filling it with false confidence in either direction, is one of the genuinely admirable things that modern cosmology does. We mapped the edge of what we can know with extraordinary precision, and then we said, clearly and without embarrassment, that beyond this edge, we do not know. That is not a weakness. It is the most intellectually honest position available to any observer in any galaxy, in any corner of the cosmos. And, in its own quiet way, it is one of the most interesting things the universe has ever offered to anyone lying in the dark and thinking carefully about it. The edge of the observable universe is not the edge of reality. It is the edge of what this particular moment in cosmic history allows us to see. Beyond it, the universe continues. In what form? To what extent? Unknown. Above you, right now. The observable portion of it sits patiently in the dark, as it has for nearly 14 billion years. The cosmic microwave background is arriving at your location from every direction simultaneously, right now, at this very moment, as it has been every moment of your life and every moment of every life before yours. The oldest light in the universe is falling on you tonight. Let that settle gently, and, when it has, we will try to count what it contains. There is a particular kind of number that stops behaving like a number. You know what one feels like. 10, 100, even 1,000, because you have experienced those quantities in ordinary life. 1,000 days is roughly 3 years. 1,000 people fill a medium-sized concert hall. The number has texture you can hold. 1,000,000 is harder. Most people have never counted to 1,000,000, never seen 1,000,000 of anything arranged so the quantity is directly visible. But 1,000,000 still carries some intuitive weight. 1,000,000 seconds is about 11.5 days. 1,000,000,000 is where intuition begins to fail completely. 1,000,000,000 seconds is not 11.5 days. It is 31.5 years. If you had started counting at 1 count per second the day you were born and counted through every waking and sleeping moment of your life without stopping, you would reach 1 billion somewhere around your 32nd birthday. 1,000,000,000,000 is 1,000 billions. 1 trillion seconds is approximately 31,700 years. The last time that many seconds had passed on Earth, the Ice Age was still ongoing and modern human civilization had not yet begun. We are going to need all of this, because the number of galaxies in the observable universe is not in the thousands, not in the millions. The best current estimate, based on the most comprehensive analysis of deep field observations and galaxy evolution models available, is approximately 2 trillion. 2 trillion galaxies. Let us arrive at that number carefully, because it deserves to be approached rather than simply announced. The first serious attempt to count galaxies in the observable universe came from an image taken by the Hubble Space Telescope in December of 1995. Mission controllers pointed the telescope at a region of sky near the handle of the Big Dipper. A patch of darkness so small it would be covered by a grain of sand held at arm's length. They exposed the detectors for 10 consecutive days, collecting every photon that arrived from that tiny sliver of sky. When the image was processed, it contained approximately 3,000 galaxies. 3,000 galaxies. In a patch of sky smaller than a grain of sand held at arm's length. By extrapolating from that tiny sample to the full sky, astronomers estimated the observable universe contains roughly 200 billion galaxies. That estimate stood for 2 decades and became one of the most widely cited figures in popular science. Then, in 2016, a team led by Christopher Consolis of the University of Nottingham published a study in the Astrophysical Journal that revised the number dramatically upward. Using deep field images from Hubble combined with mathematical models of galaxy formation and evolution, Consolis and colleagues concluded that the original estimate had missed the vast majority of galaxies. Many galaxies, particularly small and faint ones in the distant universe, are too dim for even Hubble to detect directly. By modeling how many such galaxies should exist based on what we know about galaxy formation, the team estimated the true count is closer to 2 trillion, roughly 10 times the previous estimate. It is important to be clear about what this represents. It is not a direct count. It cannot be, because the majority of the galaxies it includes are beyond the detection capabilities of current instruments. It is an inference, based on well-established physics of galaxy formation and the properties of galaxies we can directly observe. The James Webb Space Telescope, which began scientific operations in 2022 and sees further and more clearly than any previous instrument, is currently providing new data that will continue to refine this estimate in the coming years. The number may shift as that data accumulates. What the science consistently supports is that the count is very large, and substantially larger than earlier estimates suggested. 2 trillion galaxies. Now let us try to feel that number by building it from what we already know. The Milky Way contains somewhere between 150 billion and 250 billion stars. Take 200 billion as a working estimate. The average galaxy in the universe is probably smaller than the Milky Way. So, use a conservative average of 100 billion stars per galaxy. 2 trillion galaxies times 100 billion stars per galaxy gives a total of roughly 200 sextillion stars in the observable universe. 200 sextillion. Written out, that is a 2 followed by 23 zeros. The comparison astronomers most often reach for is grains of sand. The estimated number of grains of sand on all the beaches and deserts of Earth is around 7.5 quintillion. A 7 followed by 18 zeros. The number of stars in the observable universe is estimated to be roughly 10,000 times larger than the total number of grains of sand on Earth. If you took every beach on Earth and covered it with sand 10,000 layers deep, the grain count would begin to approach the number of stars in the observable universe. At some point, working through numbers like these, the mind does something interesting. It stops trying to picture the quantity directly and simply registers its weight. This is not a failure of comprehension. It is the appropriate response to a number that genuinely exceeds what human cognition evolved to handle. 2 trillion galaxies does not reward attempts at literal visualization. It rewards a quieter, more receptive kind of attention. The kind that does not try to hold the number, but simply allows its scale to press gently on the edges of awareness. The way the sound of the ocean presses on you when you cannot see the water. There is a deep field image from the Hubble Space Telescope, expanded and refined over multiple observing campaigns into what became known as the Hubble Ultra Deep Field. That shows approximately 10,000 galaxies in a patch of sky smaller than 1/13,000,000th of the full sky. Each smear, each spiral, each elliptical blur of light in that image is an entire galaxy. Each one contains billions of stars. Each one has been sending its light across millions to billions of years to reach the mirror of a telescope built by a species that has existed for less than a fraction of cosmic time. When you see that image, the word many stops being sufficient. Language, built for human-scale experience, quietly runs out of road. And what fills the space where language used to be is something tonight has been building toward all along. Not understanding in the ordinary sense, something closer to stillness. Let that stillness settle now. 2 trillion galaxies, 200 sextillion stars, a cosmic web strung between them across 93 billion light-years of expanding space. And somewhere in all of it, on a rocky planet orbiting one average star, in one average galaxy, in one modest filament of one supercluster among countless others, something is lying in the dark. listening, and wondering how large all of this is. We have been walking outward for a long time now. From the ceiling above you, through the thin stripe of atmosphere, past the moon and the sun, out through the solar system to its quiet edges, then further, to the Milky Way and its 100,000 light-years, to the local group and its 10 million light-year span, to Laniakea and its 520 million light-years, to the cosmic web stretching billions of light-years in every direction, to the observable universe itself, 93 billion light-years across, containing 2 trillion galaxies and more stars than grains of sand on every beach on Earth. Now let us turn around. Let us find the Milky Way again inside all of it, and see what it looks like from out here. The Milky Way is one galaxy among approximately 54 in the local group. It is one of the 2 largest, alongside Andromeda. In the hierarchy of the local group, the Milky Way is significant. A dominant gravitational presence, a large spiral with a rich history and a collection of satellite galaxies, a structure that has been assembling itself for most of the age of the universe. Step back to the scale of Laniakea. Now, the Milky Way is one galaxy among roughly 100,000. It sits in the outer regions of the supercluster, far from the gravitational core where the most massive clusters concentrate. In the context of Laniakea, our galaxy is a quiet resident of the suburbs, far from the center, unremarkable in position. Step back further to the scale of the cosmic web. Now we are looking at a structure containing hundreds of thousands of galaxy clusters and superclusters stretching across the full 93 billion light-year span of the observable universe. At this scale, Laniakea is one node among many. The Milky Way, inside Laniakea, inside a filament of the web, has become too small to individually identify. It is part of a texture, a statistical distribution of matter across the largest canvas that exists within our knowledge. At the scale of the full observable universe, containing 2 trillion galaxies, the Milky Way is 1 in 2 trillion. 1. Now, here is the question this entire journey has been building toward. How big is the universe compared to our galaxy? The Milky Way is approximately 100,000 light-years across. The observable universe is approximately 93 billion light-years across. Divide 93 billion by 100,000. The observable universe is approximately 930,000 times wider than the Milky Way. Nearly 1 million times wider. If the Milky Way were a single floor tile, you would need roughly 930,000 of those tiles laid end to end to span the observable universe. But width is only one dimension. Volume scales as the cube of the linear dimension. 930,000 cubed is approximately 800 billion billion. The observable universe has a volume roughly 800 billion billion times larger than the volume of the Milky Way's disk. That number will not become more comprehensible by being read again. What it indicates, more than any specific value, is a relationship that ordinary language was not built to express. The Milky Way, relative to the observable universe, is not small the way a room is small compared to a city. It is small in a way that requires a different category of thought entirely. The Milky Way is not small. The universe is large. These are not the same statement. And confusing them is one of the most common ways the scale of the cosmos gets misread. Consider what the Milky Way actually is. A structure containing up to 250 billion stars, spanning 100,000 light-years. With a gravitational reach extending hundreds of thousands of light-years further into its surrounding dark matter halo, a history spanning most of the age of the universe. A supermassive black hole photographed directly for the first time just a few years ago. Regions of active star formation alongside regions of ancient silence. An architecture that took billions of years of gravitational physics and stellar chemistry to assemble, and that is still assembling today. The universe being large does not make any of that less extraordinary. It makes the universe more extraordinary. Both things are true. Neither diminishes the other. Every measurement of the observable universe was made from inside this galaxy. Every instrument that read the cosmic microwave background, mapped the cosmic web, measured the redshift of 2 trillion galaxies, was built on one of its planets, operated by minds that grew up under its stars. The Milky Way is not the backdrop to tonight's journey. It is the place from which everything was found. 1 in 2 trillion. The only home we have ever known. The place from which everything else was discovered. These 3 things are equally true, holding all 3 at once, without letting any one crowd out the others, is what it means to actually understand the answer to tonight's question. Breathe slowly. Let the ratio settle. 930,000 times wider. 800 billion times larger in volume. 1 in 2 trillion galaxies. And outside your window, or above your roof, right now, the Milky Way is there. You cannot see most of it from where you are. The center is hidden by dust and distance. The full shape of the spiral arms is invisible to any eye, because we are inside them. But on a dark night, in a dark place, away from city lights, you can see the band of it, that soft river of blended starlight crossing the sky. That river is our galaxy, our address, our one location in a universe of 2 trillion. It is, by any honest measure, an extraordinary place to be. There is a question that naturally rises after everything we have covered tonight, and it is the kind of question that deserves to be asked carefully rather than answered quickly. If the observable universe is 93 billion light-years across, and if that boundary exists, not because space ends there, but because light has not had enough time to reach us from beyond it, then what lies on the other side of that horizon? The honest answer, stated plainly, is that we do not know, and depending on how the universe is structured, we may never know in any direct observational sense. The horizon is not a temporary limitation waiting to be overcome by better technology. It is set by the age of the universe and the speed of light. 2 quantities that do not change. No telescope, however powerful, can show us what light has not yet had time to bring us. But science does not simply stop at the edge of what can be directly observed. It builds models, tests them against what is accessible, and then carefully extends them beyond. What those models suggest about the universe beyond our horizon is genuinely interesting, as long as we hold it clearly as inference rather than established fact. The first thing the models address is geometry. Is space curved, so that traveling far enough in one direction would eventually bring you back to where you started? The way walking in a straight line on the surface of Earth eventually returns you to your starting point? Or is it flat, extending without curvature in every direction? Or does it curve the other way, opening outward like the surface of a saddle? This question can be addressed through observation. The way sound waves propagated through the early universe before the cosmic microwave background was released left a characteristic pattern of temperature fluctuations in that background radiation, with a preferred angular scale that depends sensitively on the overall geometry of space. If space is curved, that preferred scale appears either larger or smaller than it would in a flat universe. The Planck satellite produced the most precise measurements of the cosmic microwave background to date. Those measurements are consistent with a spatially flat universe. Within the precision of the observations, a flat universe is mathematically consistent with being infinite, though it does not require it. If the universe is truly infinite and flat, it extends without boundary beyond our horizon in every direction. More galaxies, more filaments and voids, more stars and planets, and whatever else the universe has been producing for nearly 14 billion years, in a volume with no edge and no end. Some cosmologists argue that in a truly infinite universe, every physically possible arrangement of matter will exist somewhere. This is a legitimate extension of the geometry measurements, held as theoretical reasoning rather than confirmed observation. It is the kind of idea that rewards sitting with rather than rushing past, not because it can be verified, but because it honestly represents the outer edge of what current science can responsibly say about what might lie beyond what we can see. Other frameworks go further. The theory of cosmic inflation, first proposed by Alan Guth of the Massachusetts Institute of Technology in 1981 and developed substantially since, proposes that the very early universe underwent a period of extraordinarily rapid expansion in a tiny fraction of a second. Inflation is supported by observational evidence, most notably its predictions about the pattern of fluctuations in the cosmic microwave background, which the Planck satellite measured with considerable precision. Some versions of inflation theory suggest the process may not stop everywhere simultaneously, potentially producing separate regions, each with their own properties, embedded in a background of still inflating space. This scenario is sometimes described as a multiverse of bubble universes. These ideas are pursued seriously by physicists at major institutions and published in peer-reviewed journals. They are also currently beyond direct observational confirmation. No observation we can make from inside our observable universe can confirm or refute the existence of other such regions, because they are separated from us by space that light cannot cross. They are seriously considered theoretical possibilities, not established features of the cosmos. What we can say with confidence is this: the observable universe is not thought to be the entirety of what exists. The full universe is very likely larger. How much larger? In what form? With what contents? We cannot say. Holding that uncertainty honestly, without filling it in either direction with more confidence than the evidence allows, is one of the genuinely admirable things that modern cosmology does. We mapped the edge of what we can know with extraordinary precision. We described it in extraordinary detail, and then we said, clearly and without embarrassment, that beyond this edge, we do not know. That is not a weakness. It is the most intellectually honest position available. And, in its own quiet way, it is one of the most interesting things the universe has ever offered anyone lying in the dark, thinking carefully about it. An edge to knowledge that is not a failure of curiosity, but a feature of the cosmos itself. A horizon that exists, not because we have stopped looking, but because the universe is only 13.8 billion years old, and light takes time to travel. The oldest light in the universe is falling on you tonight from every direction simultaneously, beyond the edge of where it came from. More universe. In what form? Unknown. But within what that light has had time to show us, there is already more than enough to occupy a very long night. Let that settle gently. And when it has, there is one more thing to understand about the universe that changes the picture in a fundamental way. Everything we have mapped so far is only 5% of what is actually there. Every galaxy we have talked about tonight, every filament of the cosmic web, every star that has ever burned, every planet that has ever formed, every atom in your body and in every body that has ever existed on this world or any other, all of the visible, detectable, measurable matter and energy in the observable universe. 5%. The other 95% is composed of two things we cannot see directly, cannot touch, and do not fully understand. One of them holds the visible universe together. The other is driving its expansion. These are not fringe ideas. They are among the best supported conclusions in modern physics, confirmed by multiple independent lines of evidence across decades of observation by different teams using different instruments with different methods. The universe is mostly invisible, and the invisible portions are not minor adjustments to an otherwise clear picture. They are the dominant components of everything. Let us begin with the one that holds things together. Dark matter is the name given to a form of matter that does not interact with electromagnetic radiation. It does not emit light, reflect light, or absorb light. It is invisible to every telescope that detects the electromagnetic spectrum, which means every telescope ever built. It interacts with ordinary matter only through gravity. And gravity, it turns out, is enough to leave a very clear and consistent record of its presence. The first strong evidence came from observations of how galaxies rotate. In our solar system, outer planets move more slowly than inner ones because they feel weaker gravity from the central mass. You would expect something similar in a galaxy, with stars in the outer regions moving more slowly than stars closer to the center, where most of the visible mass sits. When astronomers began measuring the actual rotational velocities of stars at different distances from galactic centers, starting with careful work by Vera Rubin and Kent Ford at the Carnegie Institution of Washington in the 1970s, they found something unexpected. The outer stars were not slowing down. They were moving at roughly the same speed as stars, much closer to the center, and in many cases, faster than the visible mass alone could explain. The rotation curves of galaxies were flat where they should have been declining. Something invisible was contributing to the gravitational field of every galaxy studied, distributed in a large halo extending well beyond the visible disk. This was not a single measurement. It was found in galaxy after galaxy, confirmed by multiple independent teams using different instruments over decades of work. Beyond rotation curves, dark matter's influence appears in galaxy clusters. The velocities of galaxies moving within a cluster are consistently too high to be explained by the gravity of visible matter alone. Clusters would fly apart if only what we can see were holding them together. Gravitational lensing. The bending of light from background objects by the gravity of a foreground cluster provides another independent confirmation. Calculations of total cluster mass from lensing consistently give values far larger than visible matter accounts for. Perhaps the most visually compelling evidence came from an object called the Bullet Cluster. Two galaxy clusters that had recently passed through each other. During the collision, the hot gas of the two clusters was slowed and distorted by electromagnetic interactions between particles. The dark matter halos of the two clusters, interacting only through gravity, passed through each other largely undisturbed. The result was a clear spatial separation between where the ordinary matter ended up, mapped by its X-ray emission, and where the total mass was concentrated, mapped by gravitational lensing. The mass and the light did not coincide. A study by Douglas Clough and colleagues published in 2006 in the Astrophysical Journal Letters is widely considered one of the most direct pieces of evidence for dark matter as a physically distinct component of the universe. What dark matter actually is remains one of the most important open questions in physics. Despite extensive searches at particle accelerators, including the Large Hadron Collider at CERN in Switzerland, and in dedicated underground detectors designed to catch rare interactions with ordinary nuclei, no dark matter particle has been directly detected as of the current state of science. The search is ongoing. The absence of direct detection is not evidence that dark matter does not exist. It tells us that whatever dark matter is, it interacts so weakly with ordinary matter that catching it directly is extraordinarily difficult with current technology. Dark matter makes up approximately 27% of the total energy content of the universe, according to Planck satellite measurements. Ordinary matter, the atoms that stars and planets and you are made of, accounts for approximately 5%. The remaining 68% is dark energy. Dark energy does something that has no intuitive analog in daily experience. It causes space to expand at an accelerating rate, not by pushing galaxies through space, by being a property of space itself, an energy inherent in the vacuum that does not dilute as the universe grows. As expansion creates more space, more dark energy exists, and the expansion accelerates further. The discovery of this acceleration was made in 1998 by two independent research teams. The High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, and the Supernova Cosmology Project, led by Saul Perlmutter. Both teams were studying a specific type of supernova produced when a white dwarf star in a binary system accumulates too much mass and explodes in a thermonuclear detonation. These explosions have a characteristic peak luminosity that can be calibrated and used as standard candles across cosmic distances. Both teams independently found that distant supernovae were dimmer than expected, meaning they were further away than a decelerating universe would predict. The expansion was not slowing down. It was speeding up. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011. The simplest model of dark energy treats it as a constant energy density inherent in the vacuum, called the cosmological constant. Originally introduced by Einstein in 1917 and later set aside, it returned as the most economical explanation for the observed acceleration. It fits the current observational data very well. It also raises a profound theoretical question. When physicists calculate from first principles what the energy density of the vacuum ought to be, the predicted value differs from the observed value by an enormous margin. Understanding why dark energy has the value it does is one of the deepest unsolved problems in theoretical physics. Ongoing and planned surveys, including the Euclid satellite operated by the European Space Agency, are designed to measure the expansion history with greater precision, to test whether dark energy is truly a constant or whether it evolves over cosmic time. Now, step back and hold the full picture. The universe we can see with all our instruments is 5% of the total. The gravity that holds galaxies together and shaped the cosmic web is dominated by a form of matter we have never directly detected, the expansion of the universe, which will eventually carry most of the observable cosmos beyond our horizon, is driven by a form of energy inherent in the vacuum, whose fundamental nature remains unknown. We are living inside something we understand only in part. This is not cause for frustration. It is cause for a particular kind of awe. Science has traced the outline of what it cannot see by the way it bends and shapes everything around it. Two separate, invisible things, each inferred through their effects, each confirmed by multiple independent methods, each still yielding their deeper nature slowly and only under sustained and patient investigation. The stars above you tonight are the minority. The dark is the majority, and the dark is doing something, at every scale throughout the cosmos, that the light alone will never fully reveal. Let that settle as your breathing slows. 5% visible, 95% still being understood. The universe is far larger and stranger than its light alone suggests. Everything we have explored tonight could easily be mistaken for a fixed picture, a map with edges and labels and distances that stay where they are. The universe is not a map, it is a process. And that process, 13.8 billion years after it began, is still very much underway. Space itself is expanding, not in the way a balloon expands, with a surface growing larger. The fabric of the cosmos is growing. New space is being created continuously, in the gaps between galaxy clusters, between filaments, between the great empty voids of the cosmic web. And as that space grows, the distances between unbound objects increase. Not because those objects are moving through space away from each other, but because more space is appearing between them. Edwin Hubble measured this systematically in 1929. The rate of expansion is expressed through what is called the Hubble constant. The precise value of this constant has been the subject of considerable scientific attention in recent years. Different methods of measuring it give slightly different answers. A discrepancy physicists call the Hubble tension, considered one of the most important unresolved questions in current cosmology. Measurements cluster around 67 to 73 kilometers per second per megaparsec. The tension between values obtained from early universe observations, like the cosmic microwave background, and late universe measurements, like Cepheid variable stars and supernovae, is real and is being actively investigated at multiple institutions. It may point toward new physics not yet accounted for in current models. Then, in 1998, came the discovery that changed the long-term picture of the cosmos. The expansion is not slowing down under the mutual gravity of all the matter in the universe. It is speeding up. We covered this through dark energy in the last chapter. What is worth dwelling on here is what acceleration means for the future. As expansion accelerates, distant galaxies recede faster and faster. Some galaxies are already receding faster than light, not because they are moving through space at that speed, but because the volume of space between us and them is growing so rapidly over billions of years. more and more galaxies will cross what is called the cosmological event horizon, beyond which their light can never reach us, regardless of how long we wait. They will vanish from our observable universe permanently. Astronomers estimate that the number of galaxies currently within our observable universe that will remain accessible in the far future, assuming dark energy continues at its current value, is roughly 100 billion, down from the 2 trillion currently visible. The remaining 1,900 billion will, over tens of billions of years, recede beyond the horizon one by one, their light redshifting to longer and longer wavelengths until it fades below any possible detection. And then they will simply be gone from any sky forever. This is not a sudden event. It is a slow dimming playing out over timescales that dwarf the current age of the universe. But it is real, and it is already underway. There is a further consequence operating on even longer timescales. Stars are not permanent. The most massive burn for only a few million years before exploding as supernovae. Stars like our Sun burn for around 10 billion years. The smallest, dimmest red dwarf stars burn so slowly they can persist for trillions of years. But even red dwarfs eventually exhaust their fuel. The current era of the universe, in which stars are actively forming and burning and illuminating the cosmos, is sometimes called the stelliferous era by cosmologists who study the long-term future. It began with the formation of the first stars a few 100 million years after the Big Bang. It is expected to continue for roughly 100 trillion years. We are early. Think about what that means for a moment before continuing. The current age of the universe, 13.8 billion years, represents less than the first fraction of a percent of the stelliferous era. The era of stars has barely begun. Everything our civilization has ever observed, every galaxy mapped, every supernova detected, every measurement of the cosmic microwave background, represents the opening pages of a story that will continue for timescales incomparably longer than anything yet elapsed. After the stelliferous era ends, the universe will enter a long sequence of progressively quieter epochs. Star formation will cease as gas is consumed and not replenished. Existing stars will burn out one by one. Black holes will dominate the gravitational landscape over immense time scales. Even black holes will slowly lose energy through a quantum mechanical process called Hawking radiation, first predicted by Stephen Hawking in 1974. The universe will grow colder, darker, and more diffuse across stretches of time that make the current history of the cosmos look like the first sentence of a very long book. The ultimate fate depends significantly on the properties of dark energy, which are not yet fully known. If dark energy remains constant, expansion continues forever. If it increases over time, expansion could eventually become so rapid that it tears apart not just the cosmic web, but galaxies, then solar systems, then atoms. Current measurements favor the constant scenario, but the precision required to be certain is still being developed. What is clear is that the universe of today is not the universe of the past, and not the universe of the distant future. The cosmos is a dynamic system in a particular phase of a very long evolution. And the phase we are in right now, the one that produced the conditions for stars and planets and everything observed tonight, represents an early chapter rather than a settled middle. I find something genuinely affecting about where that places us. The universe is old enough that stars and galaxies have had time to form and evolve into the richly structured cosmos we observe. Young enough that the accelerating expansion has not yet carried most of that structure beyond our horizon. The cosmic microwave background is still accessible. The cosmic web is fully formed and visible in its entirety. 2 trillion galaxies are currently available for study. Earlier, this complexity did not exist. Later, much of it will no longer be visible. We are looking out at the cosmos through a window that is neither too early nor too late. A window that will not always be open in this form. Take a slow breath. The universe is still growing. It will continue growing long after any observer currently alive has ceased to exist. And yet here, in this particular moment, something is lying in the dark, able to look outward across 93 billion light-years and piece together the story of how everything got here. That is not a small thing to have happened anywhere in the cosmos. We have spent most of tonight moving outward, adding zeros to distances, stepping back from one scale to the next until the Milky Way became one tile in a floor of 2 trillion tiles. And the floor itself became one level in a structure whose full extent we cannot see. This chapter does not move outward. It moves inward, back toward the room you are lying in, and toward a question the outward journey inevitably raises. What does it mean to be here, in a universe this large? This is not a question with a single scientific answer. It sits at the boundary between what science measures and what the mind does with those measurements. So let us be clear from the start. What follows is a set of honest observations about the relationship between scale and meaning, offered not as conclusions you must accept, but as thoughts you might carry into sleep. The first observation is one that has been circling tonight without being named directly. Size and significance are not the same thing. The universe is large. The Milky Way is small relative to the universe. You are small relative to the Milky Way by a margin so large the comparison barely functions. And yet none of that arithmetic says anything about whether you, or the Milky Way, or any particular corner of the observable universe, matters in any meaningful sense. Significance is not a physical quantity. It does not scale with volume. The universe being large does not make the local small in any way that matters. It makes the universe more remarkable. Both things are true simultaneously. Neither diminishes the other. The second observation is about where you came from, and it is one of the most genuinely strange facts in all of science, once you let it fully land. The hydrogen in your body was made in the first minutes after the Big Bang, forged when the universe was hot enough for nuclear fusion to occur throughout all of open space. The heavier elements, the carbon in your cells, the oxygen in your lungs, the calcium in your bones, the iron in your blood, were built inside stars, forged in stellar interiors through the same nuclear processes that make stars shine, then scattered into space when those stars ended their lives in supernova explosions. That enriched gas drifted and cooled and gathered under gravity into new clouds, new stars, new planets, including this one. The atoms that make you up are not from here originally. They are from out there, from stars that lived and died before the sun existed, from processes that began nearly 14 billion years ago in conditions nothing like the quiet room you are lying in right now. When you look at the night sky, you are not looking at something foreign and remote. You are looking at the process that assembled you. The factory that made every atom in your body is still running, in the cores of stars burning in the Milky Way right now, forging the elements that will eventually become part of worlds that do not yet exist. You are made of the oldest material in the observable universe. You are, in the most literal sense available, a product of the cosmos looking back at itself. The third observation is the simplest, and it is the one I want to leave you with before the final chapter. The universe being large does not make the local small. It makes the local more remarkable. The specific conditions that produce this planet, this chemistry, this moment, required an enormous amount of cosmic history to set up. Nearly 14 billion years of stellar evolution, creating and distributing the heavy elements. 4.5 billion years of planetary geology, creating the conditions for complex chemistry. Billions of years of biological evolution, producing the nervous systems capable of experiencing any of this at all. None of it was inevitable. None of it was promised by the laws of physics alone. It happened. Here, in this specific galaxy, at this specific address, at this specific moment in the long history of the cosmos. And the result is tonight. A room, a person lying in it, a sky full of light from 2 trillion galaxies, most of it traveling for billions of years to arrive at something capable of recognizing it as light from other worlds, and wondering what it means. There is a quality of attention that the scale of the universe invites. Once you have sat with it long enough, it is not awe in the way a sudden loud sound produces awe. It is quieter, more like the feeling of being in a very large, very old place late at night, when the crowds have gone and the accumulated time of the place begins to press gently on the edges of the present moment. The universe is very large, very old, and you are briefly inside it, awake enough to notice. That noticing is not nothing. In the long, largely silent history of the cosmos, the moment when matter first arranged itself into something capable of looking back at the whole and asking questions about it, may be one of the rarest things to have happened anywhere. We do not know how rare. That is the honest position. But the scale of the universe does not make the question smaller. If anything, it makes the question of what awareness means in a cosmos, this vast one, of the most interesting questions the cosmos has ever contained. Let your eyes stay closed. Let the numbers drift gently into the background. Not forgotten, but no longer pressing. You are made of ancient stellar debris, lying on a planet orbiting one star among 200 billion, in a galaxy among 2 trillion, in a universe still expanding, still building, still running the experiment. It began nearly 14 billion years ago, and all of that is true at the same moment as this room, this ceiling, this breath. Both scales are real. Both are yours. The journey is almost over, from the ceiling above you, through the thin stripe of atmosphere, past the moon and the sun, through the solar system to its quiet edges, to the nearest star, 4.24 light-years away, then out through the Milky Way, 100,000 light-years of stars and ancient light, to the local group and its 10 million light-year span, to Laniakea, 520 million light-years across, falling slowly toward the great attractor, to the cosmic web with its filaments and voids, to the observable universe itself, 93 billion light-years across, containing 2 trillion galaxies, 5% of which is the visible matter we can detect and study. And then we turned around and came back. You do not need to carry the numbers into sleep. Numbers are scaffolding. They help you build a picture. And once the picture is standing, the scaffolding can come down. What matters is not that you remember 93 billion or 2 trillion or 5%. What matters is the feeling those numbers built. And that feeling does not leave when the numbers fade. So let them fade now. Keep only a few pictures, if anything at all. The solar system as a grain of sand orbiting an orange on a kitchen table, with the nearest star, another orange, sitting a mile away across a gap of almost nothing. The Milky Way, stretching 100,000 light-years, a span that defeats every comparison we tried to make with household objects. The local group, a gravitational family of 54 galaxies, held together against the expansion of the universe by their mutual pull. Laniakea, 100,000 galaxies falling toward a center 250 million light-years away, a structure that had no name until 2014. The cosmic web, a spider's silk strung with dewdrops in the early morning light. Each droplet a galaxy cluster, the threads stretching for hundreds of millions of light-years in every direction. And the observable universe, 93 billion light-years across, containing 2 trillion islands of light surrounded by dark matter and threaded with dark energy, expanding in every direction at once. Still growing, still building, still early in the long story of what it is becoming. And somewhere in all of that, one spiral galaxy, in one quiet arm of that galaxy, one middle-aged star, around that star, at a particular distance that keeps water liquid on the surface, one rocky planet. On that planet, tonight, one room, one ceiling, one slow breath. The universe is not waiting for you to finish thinking about it. It is doing what it has always done, quietly and on its own schedule, without requiring an audience. It was doing this before there were eyes to see it. It will be doing this long after tonight is a memory that no one is left to hold. But tonight, for a little while, it had one. You followed it from this room to the edge of everything observable and back. You let the numbers press gently on the edges of awareness, and you did not look away. The cosmic microwave background arrived at your location from every direction tonight, as it has every night of your life. The Milky Way turned, as it has for 13 billion years. 2 trillion galaxies continued their slow recession into a universe that is still expanding, still dark at its majority, still only partly understood. And you were here for it. Now the journey is over, and the numbers can rest, and the only thing left is the smallest and most ordinary thing in the world. Let the day go. Let the questions go with it. They will be there in the morning, patient as light from distant galaxies, and they will not mind being set down for now. Above the roof, the Milky Way is there right now. You may not be able to see it, depending on where you are and how much light surrounds you, but it is there. 100,000 light-years of stars, most of them quiet and middle-aged and burning steadily, as they have for billions of years, as they will continue long after any particular night is over. The nearest star beyond our own, Proxima Centauri, is there too, 4.24 light-years away. The light leaving it right now will not reach your eyes for more than 4 years. By the time it arrives, tonight will be a memory. And the 2 trillion galaxies, each one carrying its billions of stars, are out there in the dark, most too far to see, some already receding beyond the horizon, their light on the way to being lost forever, all of them surrounded by invisible dark matter, threaded through with dark energy, embedded in a cosmic web that formed from fluctuations smaller than anything human-built instruments have ever measured. All of it out there, right now, quiet and vast and not going anywhere tonight. 93 billion light-years of universe, and all of it surrounding one small room where someone is drifting slowly towards sleep beneath an enormous sky. The sky is not empty. It never was. Rest now.